Hello everyone. Today we are going to begin our study of number systems with the topic of inductive and deductive reasoning. Now these are two types of critical thinking skills, and scientists, mathematicians, and experts in other subject areas often use these two methods, to make broad conclusions, generalizations, to formulate theories, and even come up with new formulae. So, in this chapter, we will talk about these two types of reasoning, understand what they are, and also how we can apply these two critical thinking skills in our day-to-day lives, right? So the first part of this lecture is going to be devoted to understanding and using inductive reasoning and solving problems using this type of reasoning. And the second part, we are going to talk about understanding and using deductive reasoning and applying them to solve problems. Now, before we go further into talking about the two types of reasonings, we need to understand what natural numbers are. Now, natural numbers are also known as counting numbers. Those are numbers that we use to count something. And when we count something, say number of books or number of students in a class, we start with the number 1, correct? We do not start with 0, 1, 2, 3. We start counting from 1. So the set of natural numbers or counting numbers begins with the number 1, and they are all positive integer values. So 1, 2, 3, 4, 5, 6, 7, 8. And you see over here these three dots, which are also called ellipses, spelled Ellipsis, ellipsis. These three dots tell us that the numbers continue beyond 8. So 8 is not the last number where we stop, but it keeps going, and the numbers are positive integer values higher than 8. All right. So the three dots, they are called ellipses. It means that 8 is not the last number. The set does not end here, but it keeps continuing. All right. So with that understanding of counting and natural numbers, we can now talk about inductive reasoning and some examples of it, and we will be using these counting numbers to illustrate some examples of inductive reasoning. Now, one other terminology that we will be using in the course of this lecture is called divisibility. So let's try to understand what divisibility is and what we mean by divisibility. So if A is divided by B, has a remainder of 0, then A is divisible by B. So let's say we take a number which is 12, all right, and we divide it by 4. So 12 divided by 4, if we do perform this division, we get 3, right? 4 threes are 12, and 3 is called the quotient, and the remainder is 0. Correct? 12 minus 12 is 0. Remainder is 0. And when that happens, when we get a remainder of 0 after performing a division, then we say that particular number is divisible by the number we divided by. So 12 is divisible by 4. That means 4 divides 12 completely without leaving any leftovers or remainders, right? So that's what being divisible is. Now the counting numbers that are divisible by 2 are 2, 4, 6, 8. So the entire set of counting numbers, whenever it's divided by the number 2, then the result is uh, are all even numbers, all right? So these numbers are the even counting numbers, all right? So counting numbers that are divisible by 2 are all the even numbers. So if we take all the even numbers and divide it by 2, we'll always get an answer of or rather we will always get a remainder of 0, and those are called even counting numbers. The counting numbers that are not divisible by 2, that means the numbers will leave a remainder. Those numbers are called odd counting numbers. So the odd counting numbers 1, 3, 5, 7, 7 divided by 2 leaves a remainder of 1, right? 9 divided by 2 leaves a remainder of 1. So it's not divisible by 2. Those are the odd counting numbers. Now let's try to understand what the process of inductive reasoning is about. Now in inductive reasoning, we move from parts to the whole. All right, from parts to the whole. That means we start with a specific number of cases, we study specific number of cases, and then we make observations on those cases. We try to identify patterns, commonalities, similarities, or differences, whatever it may be. So we observe those patterns, and then once we think we have observed quite a few of those cases, we go on to making conclusions, generalizations on the rest of the cases, even though we may not have seen them or those cases haven't been presented to us. Based on the pattern we have observed on a specific number of cases, we make a conclusion about the rest of the cases, and we try to get an idea of how the other cases are going to be. All right, so here it says the process of reasoning to a general conclusion through observations of specific cases. So we start with a specific number of cases. All right, that's why I said parts. Those specific cases are a part of a greater universe of cases, and we observe them, we look out for patterns among those cases, and then based on those observations, we decide or come to a conclusion that the rest of the cases must also be following the same pattern. So that's what inductive reasoning is about. All right, we also call the process as the process of induction. And scientists use this process a lot, mathematicians too, to come up with answers to complex problems, as well as to come up with theories, formulas, and so on, right? Now, as we said before, the inductive reasoning method is a method applied in the field of science and mathematics a lot, and it is a part of the scientific method. Now, when we make generalizations, when we make predictions based on specific observations, it's also called hypothesis or conjecture. All right, so we will be using the word conjecture later on in some of the uh, question problems that we will work on. So it's important to know the meaning of conjecture. So when we make a broad generalization based on patterns identified among specific cases, we call that a conjecture or also a hypothesis, right? Now, one area of application of inductive reasoning in the real world is in the case of fingerprint identification, right? Now, there are 8 billion people in this world, all right? It's not possible to have taken the fingerprints of every person. So, what was done probably is that they looked at a few million fingerprints and found that no two fingerprints were the same. Every fingerprint in those 1 million or however many they may have studied, they were different, they were unique. All right, and based on that recognition, that pattern recognition that every fingerprint that we looked at was unique, we can conclude that the rest of the population will also have fingerprints that are unique from each other. All right, so that is a real life application of inductive reasoning. So to the question on the fingerprint problem, to which we already provided the answer of how inductive reasoning is being used, they've put a solution together here. It says in millions of tests, no two people have been found to have the same fingerprints or DNA. By induction, then, we believe that fingerprints and DNA provide a unique identification and can therefore be used in a court of law as evidence. Is it possible that sometime in the future two people will be found who do have exactly the same fingerprints or DNA? All right. So what they're saying is that, yeah, we have studied maybe 1 million fingerprints and we found that every fingerprint is unique, and based on that, we can safely conclude or used inductive reasoning to come to the conclusion that the fingerprints, everybody's fingerprints is unique, even the ones that were not in our study. All right. Now, however, is it possible that out there are two fingerprints which will be exactly the same? Right? The pattern of the fingerprints, the DNA pattern will be the same. Yes, right? It is possible. We will never know that unless we stumble on it someday. But in spite of it, the vast million and billions of fingerprints are still assumed to be unique based on inductive reasoning. Now, another example of inductive reasoning is where we are asked to pick a number and then perform certain operations and then go through a process, and then the person tells you what the number you had guessed, right? Where maybe some time in the past someone may have shown this to you as a magic trick where they say pick any number, then multiply that by this number, and then to the answer add this number, then subtract from it this number, and then divide, and then they surprise you by telling you the original number you had guessed. Correct? So this is an example of that, and we are going to go through that process and see how we can arrive at conclusions based on specific cases of the same exercise. So here it says pick any number, multiply the number by 4, add 2 to the product, divide the sum by 2, and subtract from 1 from the quotient. Repeat this procedure for several different numbers and then make a conjecture about the relationship between the original number and the final number. So we will go through the steps. I just read it aloud here, but in the next slide we will go through the steps where we will actually see how this is being performed step by step, right? So let's walk through the pick any number game or example that we just talked about in the previous slide, but we will go step by step here. So the first step is to pick any number. All right, so they've picked 5 here, and then it said multiply the number by 4. So whatever number you picked, you multiply that number by 4 and you get a value of 20. Then it says add 2 to the product. All right, product is the answer you get after multiplying. All right, the result of multiplying two numbers is called the product. So add 2 to the product. So they've added 2 to 20. Whatever you got as an answer in the previous step. And we get 20 plus 2 is 22. Divide the sum by 2. So 22 divided by 2 equals 11. and then subtract 1 from the quotient. Quotient is the result we get after dividing two numbers, right? So 11 here is the quotient, and we have to subtract 1 from the quotient. So 11 minus 1 is 10. And then we have to go back to the original number and see how it has changed from the initial number that we picked, and if there's any relationship between that. All right, so the initial number was 5, and after performing all these operations, we see that we got a 10, which is 2 times 5, which is double of the number we had picked, right? So it's not enough to just uh, go through one example or one number, one case, and come to the conclusion that, hey, it's going to be double. The relationship between the initial number and the end result is going to be double. You have to go through a few more cases to come to that conclusion, and then maybe we will be able to perform what's called deductive reasoning and come up with a formula. All right, but I think in the next slide we will go through another example of picking a number, and before we come to the conclusion that it's going to be double every time. All right. So after going through several trials with different numbers, they see the results. All right, so we started with the number 5. The one that we worked out initially was with the number 5 and finished with the number 10. Now if we start with the number 2, so you can do the same exercise, you can go through the same steps, the same process using different numbers. So they picked 2 and walked through the same steps. The final result was 4, which we see is double of 2. Start with 3, the final result is 6, and they did another exercise where they started with 4 and the result was 8. So in each case we see the end result is double of the initial number that was picked. So now based on these few cases that we worked through, we may conjecture that when you follow the given procedure, the number you end with will always be twice the original number. All right, so this is how we can come up, or this is how we can use inductive reasoning, and in the next slide we will see how we can go from general to special cases, which is a case of deductive reasoning. Now, in the process of inductive reasoning, there is something called counterexample. Counterexample is a special case that kind of disproves the conjecture we have arrived at. So it says here, in testing a conjecture, if a special case is found that satisfies the conditions of the conjecture but produces a different result, that case is called a counterexample. So just like when we talked about the fingerprints, we said that we test thousands or millions of fingerprints and we arrive at the conclusion that fingerprints are unique for each person. However, if someday we come across two fingerprints that are exactly alike, then that would be a case which it would be a counter example, and that would kind of disprove the conjecture. All right, so that's what a counter example is. Now we'll talk about a second kind of reasoning in critical skills or critical thinking. It's called deductive reasoning. Now in deductive reasoning, we start with a general statement or a general idea, and from it we draw specific conclusions. So deductive reasoning is the process of reasoning to a specific conclusion from a general statement. All right, so now we know about two types of reasoning. One is called the inductive reasoning, and then we have the deductive reasoning. In inductive reasoning, we start from specific cases. All right, we start with specific cases and move towards a general idea or a general statement, general conjecture. Whereas in deductive reasoning, it's the other way around. We start with a general form, a general idea, a general statement, and from it we conclude specific cases. All right, so it's the other way around, specific cases. So we are now going to use deductive reasoning to prove that the example we worked in, example 5 of picking a number and then going through all the different steps and then comparing the relationship between the final answer and the initial answer, we are going to work those steps out with a general variable. All right, so we are going to start with with a variable which we'll call n, and then we will perform the steps on that n and see the relationship between the end result and uh, the initial variable that we started with. So here we begin with a general case rather than a specific example. All right, so we start with n. All right, so you can choose any variable, you can choose x as well, but here they start with n, pick a number n, and then it said multiply the number by 4. So it's 4 times n, 4n. In the next step, we added 2 to 4n, which was the product, 4n plus 2. And in the next step, we divided the sum 4n plus 2. All right, so we better have brackets around this. 4n plus 2 should be divided by 2, and when we do the division we get 2n plus 1. All right, so and let me quickly show you how they arrived at 2n plus 1. So we have 4n plus 2 divided by 2. Right, so you could do it in two ways really. Either you distribute the common denominator to both the terms and divide, so you can do 4n divided by 2 plus 2 divided by 2, and that would give you 2n for the first term, and 2 divided by 2 is 1, so 2 times n plus 1. All right, 2 times n plus 1, and that's how they got it. Or you could factor it out. 4n plus 2 can be factored and written as 2 is common to 4 and 2. So you factor out the 2, and what you have inside brackets, 2n plus 1, correct? So when you factor, all you have to do is to get the values or get the terms inside the brackets. You take your 4n divided by the number you factored. So 4n divided by 2 is 2n, and 2 divided by 2 is 1. So that's how we got 2 times 2n plus 1. And then you can divide it, right? We have to do this division, divided by 2. So we end up with 2n plus 1. All right, so this you should be able to remember from your past algebra courses. So 2n plus 1 is what we get after dividing the sum by 2, and finally we subtract 1 from the quotient. So quotient was 2n plus 1. When you subtract 1 from 2n plus 1 and minus 1 is a 0, and you're left with 2n. So what do we see here? The relationship between the initial value and the end value. It's n was what we started with, and the final answer was 2 times whatever n was. All right, so now we can go ahead and plug in different values for n, go through this exercise, and it'll always have an end result which is double of the initial result.